Yes.
Okay, thank you. Right, so the whole content in topic 1, part A, have been uploaded in UKM Folio. There are some adjustment in the slide, in the handout. Okay, so let us continue. Okay, in this new slide, I have divided the whole, I have divided the whole topic in 3 subsection instead of about 7 subsection. Okay, where the first section is systems of linear equation. Second and 2 are methods to solve systems of linear equation using matrix. So there are going to be 2 types of matrices. That is why the topic of our the topic is systems of linear equation and matrix. Okay, so let us continue. In this first subsection, I have divided into 4 subsections, which are linear equations, solutions of linear equation, systems of linear equations, and solutions of systems of linear equation. In the previous lecture, we have discussed, hold on, we have discussed the first two, subtopics. Okay, and we are going to continue to look at systems of linear equations and solutions for systems of linear equation. Okay, so we have seen this topic. Okay, this is the general form of a system. This is the general form of a linear equation with n number of variables. Okay. And here are some examples. Solutions of linear equation. Okay, let me just do some recap. If our linear equations consist of n number of variables, let's say x1, x2, xn are the variables. Okay, therefore, the solution for the solution for the linear equation must be in n tuple. Let's see, A1, A2 up to En in R to the power of n. Okay, since it has n variables, therefore the solution, any solution for the linear equation must have n components. A1 for x1, A2 for x2, up to An for xn. Okay, such that whenever we replace A1 into x1, we replace A2 into x2, and we do that until An replace xn, then the linear equation is satisfied. Then that is why this is the solution, one of the solution for the linear equation. Okay. Okay, systems of linear equation. Okay, we have seen this. Okay. If I'm not mistaken, we stop until here, right? So we are continuing the topic with systems of linear equations. Systems of linear equation is a compilation, a combinations of some linear equations with similar number of variables. So there are finitely many linear equations where every linear equation must have similar number of variables. For example, this is a system of linear equation which has three linear equations. One, two, three, and there are two variables. X and Y. Okay. In general, we write general systems of linear equation in this form, where this systems of linear equation has m number of linear equation. First equation, second equation, up to m equation. Okay, it has m equation, and every linear equations has x1, x2, up to xn. Therefore, there are n numbers of variables. And the values here, we call it as coefficients for the correspond variable. And the values of these coefficients can be zero, any real numbers. The same goes to the constant at the right hand side. It can be zero or any real numbers. Okay, now we want to understand, or we want to understand what does it mean by solutions of system of linear equation. We do know solutions of linear equations. Now, what about solutions for systems of linear equations? We start by an example. We have these systems of linear equation, right? 3 is solution for the systems of linear equation. Okay, 3 means that x is 3 and y is 3. And whenever we substitute x with 3, y with 3, then the linear equation is satisfied, because 3 plus 3 is 6. Similar to the other linear equations, we have to check every linear equation. The solution must satisfy all linear equations. Okay. For this example of systems of linear equation, 3 is the only solution. 3 is the only solution. There is no other solution for the systems of linear equations. Okay, you may check. Or later on, in subtopic 2 and subtopic 3, we are going to see why these systems of linear equation has only one solution. Okay, geometrically, if we draw all of these linear equation 1, 2, and 3, we are going to have 3 lines. We are going to have 3 lines in xy plane. This is xy plane. XY plane because it is in 2-dimensional, because the variable, the number of variables are 2. Okay, so the solution 3 is in fact the intersection of these 3 the solution 3 is actually the point where these 3 linear equations intersect. It intersects at this point, 3, therefore 3 is solution. And there is no other intersection point, therefore 3 is the only solution. Okay, is that clear?
Yes.
Okay. Okay, so this is how we define solution of a systems of linear equation in general. Okay, so we have systems of linear equation with n variables. Therefore, the solution must be in n tuple, where it has n components. The solution must have n component. First component, second component, and up to n component. Okay. This sequence is called a solution of the systems of linear equation if whenever we substitute x1 with s1, we substitute x2 with s2, and we do the same up to xn. We substitute xn with sn, and the systems of linear equation is satisfied. Mean all of the linear equation in the systems of linear equation satisfied with this solution. Okay. For example, okay, 1, 5 is a solution for the systems of linear equation below. Okay, so since the solution here has two components, so we know that the systems of linear equation must have two variables. You may check that 1, 5, these points satisfies all three linear equations. Okay, you may check later on. Okay. Since x equal to 1 and y equal to 5 satisfy all linear equations in the systems of linear equation. But bear in mind that there might be some other solution for the systems of linear equation. There might be some other solution for the systems of linear equation. To determine that, we are going to look at subsection 2 and subsection 3. Okay. So, later on, we are going to see that there is a systems of linear equation that has no solution at all. Systems of linear equation that has no solution. And we call it as inconsistent systems of linear equation. And if there is at least one solution of the systems of linear equation, we call the system as consistent systems of linear equation. So consistent is the opposite of inconsistent systems of linear equation. Right. And every consistent systems of linear equation, there are two possibilities for consistence of systems of linear equation. There are two possibilities. It is either has unique solution or it has infinitely many solutions. Okay, there are only two possibilities for consistent systems of linear equation, which is it is either unique solution or infinitely many solution. Okay, this is quite important. This statement, the last statement is quite important. This is for consistent systems of linear equation with infinitely many solutions. Consistent systems of linear equation with infinitely many solutions must have at least one variable, okay, there are many variables, right? Whenever the system has infinitely many solutions, then we must have at least one variable, let's say variable y, where y is equal to t, and t can be any real numbers. Okay, so you may recall some linear equation which has infinitely many solutions, where we introduce a parameter. We introduce a parameter to write down the solutions for the linear equations, remember? So again here, a consistent system of linear equation with infinitely many solutions must have at least one variable, let's say a variable y, such that y is equal to t. And we call t as parameter, and the variable y is a free variable. This is quite important. Okay, is that clear?
Yes.
All right. If it's not clear, then you may ask for you may ask me to repeat. All right. T is called parameter. I'm not sure how to. Okay, I can move this around. Okay. So T is the parameter, and Y, which is correspond to the parameter T, is called free variable. Okay. For some illustrations, okay, to see the picture of systems of linear equation geometrically, let us consider a general systems of two linear equations in variables x and y. Unknowns is variables. A systems of linear equation which consists of two linear equations, first linear equation and second linear equation, where these two linear equations has two variables. There are two variables, x and y. So to see the solution for these systems of linear equation, we have to look at the intersection of these two lines, right? To see the solution geometrically, we have to draw the graph of 1 and 2, which are two lines, okay? And the solution for the systems of linear equations are the points of intersection between these two linear equations, okay? So there are three possibilities. Okay, before that, graphically, let's say L1 L1 denotes the lines for linear equation 1, and L2 is a line for the second linear equation. Okay, then the solutions are point in two tuple, two components of intersections of L1 and L2. Okay, there are three possibilities. Okay, the first possibility is whenever L1 and L2 are parallel, right? They are parallel. So we can see that there is no intersection. There is no intersection of L1 and L2. Remember, L1 represents linear equation 1 and L2 represents linear equation 2. And whenever, after we draw the graph of these two linear equations, we found that they are parallel, and therefore there is no intersection. and therefore there is no solution. Okay. The second possibility is they L1 and L2 intersect at one point. It intersect at one point. There is no possibility of intersection at finitely many points. It can't be, because L1 and L2 both are straight lines. So if they intersect finitely at finitely many points, then the point must be unique. The point must be unique. Means only one points of intersection, therefore only one solution. And the other possibility is L1 and L2 both lie on the same lines. L1 and L2 both lie on the same lines. Therefore, all points here, all points that I just draw lie on L1 and L2, and both they are solution for L1 and L2. And since there are infinitely many points here, there are infinitely many points on the lines, therefore the solution it has infinitely many solutions. Is that clear? Is that clear?
Yes, doctor.
All right. So to find a solution of a system of linear equations, we are not going to draw the graph for all cases, because we might have systems of linear equation with more than 3 variables, right? We may have systems of linear equation with more than 3 variables. For that case, we are not able to draw the graph. Okay, so what is the method to find the solutions of a systems of linear equation? I would like to recall, maybe in your school, let's say I have for x plus 2y equal to 0 and x minus y equal to 5. Let's say if we have two linear equations with two variables, okay, then to find the solution, I believe that you know how to find the solution. I believe that you did learn this in your school. I don't remember the name of the method. I don't remember the name of the method, but I believe that if I give you these systems of linear equation, you can solve it easily, right? Am I correct? Am I correct in your school level maybe? Anyone? Will you able to solve this simple systems of linear equation? No?
Yes.
How you're going to do that? How you are going to do that? Sorry. Okay, let's say we have x minus y equal to 5, and for x plus 2 equal to 3. How are you going to solve this? There are many methods, right? For example, why? For example, we may add them up, right? 1 plus 2, then we are going to have 5x equal to 8, right? Therefore, x equal to 5, right? This is one of the methods. And therefore, y is equal to x minus x minus 5. Therefore, I'm not sure what is the name of this method, but I believe that most of you know this. May I know you already know this in your school level? Anyone?
Yes. Yes.
Okay, thank
Yes.
you. And there are many other methods, right? However, if we are given more complicated systems, let's say three variables, we are able to do that by the same method, but it's going to be complicated. It's going to be complicated. So let us see how to solve more complicated systems of linear equation. Okay, by using a matrix which is called augmented matrix. Augmented matrix. The first method is solving a systems of linear equation by using augmented matrix, a matrix that represents the systems of linear equation. So roughly, here is the step-by-step methods. First of all, we compute augmented matrix for the systems of linear equation that we want to solve. Okay, and then we do something. We perform something to the matrix. We perform elementary row operation. ERO is elementary row operations. Okay. Remember that, let's say we have A, B as a matrix. Let's say A, B, C, D, and this is E, F, G, H. What are arithmetic operation on matrix? What are arithmetic operations? We have plus, right? You can do A plus B, right? We can do A minus B. We can do A times B if the size of A is m times n size and B is n times m, right? We can only do the multiplication if this is true. And the fourth arithmetic operation on a matrix is scalar multiplication. Remember, C times A, where C is any real number. So these are arithmetic operation on a matrix. But now we are going to introduce very special operation on matrix. Okay, very special operation on matrix. We call it as elementary row operation. Okay, so basically, after we get the augmented matrix of the systems of linear equation, we perform some elementary row operations. We do something to the matrix to change the matrix into new matrix. Okay, we want to change the matrix into another matrix in a very special form. We turn the original matrix, the augmented matrix, into a very special form. We call it as REF form, reduced echelon form. Reduced echelon form. Okay, there are two choices. Okay, we are either change the matrix into REF form or RREF form. Okay, you may choose, or depends to the question. If the question wants you to reduce it to REF, then we do that. Okay, so bear in mind, we get augmented matrix and then we perform some elementary row operations to change the matrix to become a very special form called REF form or RREF form. Okay, but how to do that? There is some steps. There is a method which gives us step-by-step method to change the matrix into REF form. Gaussian elimination is a method that gives us step-by-step process of changing the matrix into REF form. And for RREF form, we use another method called Gauss-Jordan elimination. Okay, and then whenever the augmented matrix already in REF form or RREF form, then we are able to get the solution easily. Okay, we are able to get the solution of the systems of linear equation easily. So these are 4 steps of solving systems of linear equation using augmented matrix. Okay, so to understand these steps, we need to understand some terms. Okay, so this is the recap. To solve a systems of linear equation using its augmented matrix, we use a method called Gaussian elimination, right? As explained earlier. The Gaussian elimination method, the aim of the method is to reduce augmented matrix to special form of a matrix, either RREF or REF form. Okay, using the steps in Gaussian elimination. Okay, in this method, in the methods of Gaussian elimination, it is involved some operations called elementary row operations. Okay, and there are 3 types of elementary row operations. Okay, is that clear?
Yes, doctor.
Okay, I hope so. I hope the previous chart, the previous picture help you to understand these sentences. Okay, these statements. All right. Then, okay. So to understand the whole process of solving the systems of linear equation using the augmented matrix, we have to understand these 4 terms. We have to understand these 4 terms: augmented matrix, RREF and REF matrix, elementary row operations, and Gaussian eliminations. We have to understand these 4 terms. Okay, First of all, augmented matrix. Okay. Every system of linear equation has its augmented matrix. We correspond each system of linear equation with a matrix called the augmented matrix. How? Let's say we have this general form of systems of linear equation. So this is a general form of systems of linear equations with m number of linear equations. M number of linear equation. One, first linear equation, second linear equation, and the last one is m linear equations. And every linear equation in this system share similar variables. They share similar variables x1, x2, up to xn. So there are n number of variables. And in this system, we also have coefficient. Right? Coefficient. So A11, A21, AM1 are coefficients for a variable x1. Okay. The coefficients are real numbers. The coefficients are real numbers. So this is in R. This also in R. This also in R. And the number on the left. They are all real numbers. Okay. From here, we are going to compute the augmented matrix. Okay. So here is the augmented matrix. We take the real numbers. We take the real numbers. The ordering of linear equation is very important. The ordering of the variables are also important. Okay, so we take all real numbers from the systems of linear equation to form a matrix called augmented matrix. Okay, the line here is to separate a coefficient with the constant on the right hand side of every linear equations. Okay, is that clear? So the numbers in the first row are coefficients of variable x1, right? And the numbers in the second row, second column are coefficients for variable x2. The same goes to column number n. They are all coefficients of xn. And on the our right side, they are constant. On the right hand side of the equation. Okay. Now, solution. Okay. Bear in mind that since it has n number of variables, solution must be in x1, x2, up to xn. Solution must have n component. Okay. Solution of these systems of linear equation must have n component, right? Because it has n variables. Okay. So augmented matrix is clear. For the systems of linear equation, here is the augmented matrix, right? So the coefficient for x1 is 1, right? That's why we have 1, 2, 3 as the first element in the first column. And then 146 in the second row, and this is, sorry, the second column, and this is in the third column. And at the right hand side, the other parameters. Sorry, they are constants. Okay, so computing augmented matrix is straightforward, but make sure that the order of the variables are always consistent. The ordering of variables must be consistent from the first equation to the last equation. Is that clear? Is that clear? Anyone? I cannot hear anyone.
Yes.
Okay, thank you. All right. Okay. Systems of linear equation. Let us consider three systems of linear equation. Okay. These three systems of linear equations has three linear equations and three variables, right? Three linear equations and three variables, x, y, z. Okay. Using online calculator, we may see that the systems of linear equation has similar solution. Okay. Using by online, you may solve the systems of linear equation easily. You can using Desmos three-dimensional graphing Desmos to draw all of the linear equation and see the intersection point. You see the intersection point, and the intersection points are the solution for the systems of linear equation. Or there is many online calculator to compute solution for a systems of linear equation. You may try Symbolab or some other online calculator. Okay, you may try later on. Okay, but from here, by the help of the online calculator, you may see that the first systems of linear equation, the second systems of linear equation, and the third systems of linear equation, they all have similar solution. Okay, they all have similar solution where the solution is unique. For this example, the solution is unique, where it is the first component, x is equal to 5, y equal to -2, and z equal to 4. Okay, you may check that. This is the only solution for all of these three systems of linear equation. Okay. Is there anything that you notice from this example? Do you notice something from this example? Anyone? If you want to say something, look at systems of linear equation number 3. X equal to 5, y equal to -2, and z equal to 4. Right? So this solution we can get directly from the systems of linear equation. Right? We can get the solution for the third systems of linear equation easily. Right? It's quite straightforward. It's straightforward. Right? What about systems of linear equation number 2? To get the solution is also not difficult because we have z equal to 4. Therefore, you may replace z with 4 and then you will get y equal to minus 2. Right? And then replacing y with minus 2, z with 4, and then you will get the value of x equal to 5. Okay, therefore from here we can see that systems of linear equation 2 is easy to solve. Easy to solve. But systems of linear equation 3 is easier compared to SLE2. But to solve this is going to be a bit difficult. We need more works to solve these systems of linear equation. All right? Is that clear? Is that clear, anyone? You may give me thumbs up.
Yes.
Right, thank
Yes.
you. All right, thank you. Okay, so this is the systems of linear equation. SLE3 has a straightforward solution. SLE2 is easier to solve compared to SLE3. Why? You have seen that. So, to solve systems of linear equation 1, we may solve systems of linear equation 2 or 3 instead, right? To find the solution for this, okay, we may solve this system or this system. That's the idea of solving systems of linear equation using augmented matrix. So, if we are given systems of linear equation in type 1, how to compute systems of linear equation 2 and 3? Okay, that's the question that we have to answer later on. Now, the augmented matrices for the three systems of linear equation. That augmented matrix for systems of linear equation 1, you may put the line there. This is augmented matrix for systems of linear equation 2 and augmented matrix of system of linear equation 3. Okay, then you have to note that B and C, B, this matrix B is in the form of row echelon form. This in REF. This matrix is in REF form. Okay. Sorry, I got a call. Can you give me just 1 minute? Hello Kak.
Umi ambil ke?
Abah. Call Abah.
Alah, abang ambil lambat.
Umi ada lecture.
Ha?
Umi ada lecture. Sekarang ada lecture.
Oh, okay. Okay, bye-bye.
Okay, call Abah Bye. Hello. Hi everyone. You still with me?
Yes, okay.
Okay, sorry. I got a call from my daughter. Do you know that during this about 1 month, we are all fasting. We call it Ramadan. During this Ramadan, my children finish their school early at 3:30. Hold on, I'm trying to set up this. Macam mana nak buat ni? Doesn't matter. Okay, doesn't matter. Okay. I want you to all right. Okay. So B is in the form of REF and C is in the form of RREF, which is reduced row echelon form. Okay. So whenever an augmented matrix in the form of REF or RREF, then the systems of linear equation can be solved easily. Okay, is that clear? Whenever the augmented matrix are in REF or RREF, then the systems of linear equations can be solved easily. Okay, so that's the idea. Okay, but the question is, what is RREF and REF? What is the form? What kind of matrix are in the form of RREF and REF? That one question. Another question is how to get B or C from A. How to get matrix B and matrix C from A. Okay. So we have two questions. Okay. So here is the answer for the first question. What's REF and REF matrix? Okay. So to solve a systems of linear equation, we need to reduce the augmented matrix to a matrix of a form either REF or RREF. You may choose or depends to the question. Okay. Okay. A matrix is in RREF if it has following properties. So we have to check the following properties. If a matrix satisfies all of these properties, then the matrix is in RREF. Okay. So the first property is if a row of a matrix does not consist entirely of zeros, entirely of zeros. Okay, for example, if I have this row, this row consists entirely of zeros. Consists entirely of zeros. Or the elements of the row are all zeros. If this is not the case, okay, that means we have a row where there are some elements in the row that are not zero. There are some numbers in the row, doesn't matter where it is, and the numbers is not zero. Okay, A, B is not zero. Then, if the row does not consist entirely of zeros, then the first non-zero number in that row must be 1. the first non-zero number must be 1. Is that clear? So the others are all zeros. Okay, the first non-zero number must be 1. Okay, and we call this as leading one. We call this number 1 as a leading one. Okay, if we have another element, number 1, if we have another element which is 1 in that row, this is not leading one. Okay, so this is not a leading one. It is very important to identify leading one. Okay, remember that it is very important to identify leading one. Is that clear? Just give me thumbs up
Yes.
if you do understand. Okay, thank you. All right. Okay. This is a row. Okay. So this is leading one. This is leading one. And we don't care what's number after leading one. The stars. We don't care. We don't mind what numbers after one. But the numbers before 1 must be 0. The number before 1 must be 0. Okay, so we have to look at every row of a matrix. We have to look at every row of the matrix. If the row not consists entirely of zeros, then we need to have a leading one for that row. Okay, if they are all zeros in entire row, in one row there is only zeros, then we don't have to find leading one. Okay, is that clear? This is an example. Okay, so look at the first row. The first row is not entirely zeros, right? And the first non-zero number is 1, right? So it satisfies property 1 for the row 1. For the second row, they are all zeros. For the second row, they are all zeros. So we don't have to identify leading one because they are all zeros. Okay? Remember that we have to consider row that does not consist entirely of zeros. And the third row, the first number, the first non-zero number is also 1. So this one and this one are leading one for the first and third row. Okay? Is that clear?
Yeah.
Thank you. Consider this matrix. Look at the second row. Look at the second row. The first non-zero number is -1, which is not 1. So leading one does not exist. Leading one does not exist. This is not leading one, because leading one is the first non-zero number in that row. Okay, so this matrix doesn't satisfy property 1. Even though row 1 and row 3 satisfies property 1, row 1 and row 3, if you notice, okay, row 1 and row 3, does contain the leading one, right? Okay, but not the second row. Therefore, the whole matrix does not satisfy property 1. Okay, is that clear? Is that clear?
Yes.
Okay, so we move to the second property. If there are rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Okay. Whenever we have rows with entirely zeros, then we put them at the bottom of the matrix. Okay. We collect them together, put them at the bottom of the matrix. Okay. This is quite easy. For example, the first row is a row that consists entirely zero. The first and the fourth. So this is not satisfies property 2, right? Because the first row must be located at the last row. They must be at the bottom. Okay. However, in this example, the last row is the row that consists entirely of zeros. So this satisfies property 2. This matrix satisfies property 2. Okay, I think that's quite straightforward. Okay, we move to the third property. In any two successive rows that do not consist entirely of zeros, the leading one in the lower row occur farther to the right than the leading one in the higher row. First of all, what are successive rows? Successive rows are two rows that next. Do you understand successive rows? Two rows that they are together, not together, following the other. Is that clear? Successive row?
Yeah, doctor.
Okay. If we have two successive rows and these two rows does not consist entirely of zeros, then they must have leading one, right? Okay. Two successive rows that are not entirely zeros, they must have leading one. Okay. This property says that the leading one in the bottom, the leading one at the lower row must be on the right of the leading one. Sorry. Okay. Leading one at the lower row must be to the right of the leading one at the upper row. Okay, is that clear? Okay, farther to the right of the leading one at the lower row, at the upper row. Example. So firstly we need to identify row which is not entirely zeros. Okay, so there is no rows with entirely zeros. Therefore, we need to identify the leading one. So here is the leading one. Right? Here are leading one for rows 1 to 4. First of all, let's compare 1 and 2. Two successive rows. So since leading one at the lower row is located at the left side of the row at left side of the leading one at the upper row, then these two rows doesn't satisfy property 3. Right? Is that clear? Is that clear?
Clear.
It does not satisfy property 3. Okay. In the second row, second matrix, these are leading one, right? So we can see that leading one at the lower row is located to the right of the leading one at the lower row. Okay, is that clear? So this satisfy but not this. So that the third property. I think this is the last property. Okay, now we look at column. Now we look at each column. Each column that consists a leading one has 0 everywhere else in the column. We look at every column. We look at every column. If that column has a leading one, doesn't matter where. If that column has a leading one, then the other numbers must be zeros. Okay, let's say this one has 1 there. The others must be zeros. Okay, is that clear? Thumbs up if you do get it. Anyone? You don't want to give me a thumbs up. Anyone? Any thumbs up? No? So you don't understand? You don't really get it? Hello?
Clear, doctor.
Yeah. What about the others? What about the others? I hope you do get it. If you don't get it, just give me this symbol if you don't get it. Okay, thank you for the thumbs up. Okay. Okay, example. Okay. So first of all, we have to identify a leading one. The one in red color are leading one. So for the first row, every other elements are zeros. But at the second row, there are two leading one. So this is not satisfy property 4. Okay, because if it has in one column, there must exist only one leading one. Cannot have more than one leading one. So that's not correct. And you have to note that this is not leading one. This is not a leading one. Why? Because this is not the first non-zero that appear in the row. This is not the first non-zero number that appear in the row. Okay. And in this matrix, okay, we have the red one is the leading one, and it obvious that every other elements in the row is zero, are zeros. Okay, so this is satisfies property 4. Okay, right. Okay, so if a matrix satisfies property 1, 2, 3, and 4, then they are in the form of reduced row echelon form, RREF. Okay, if a matrix satisfies all 4 conditions, then the matrix is in the form of RREF. And if the matrix satisfies only the first 3 conditions, then the matrix is in REF. So for REF form, it must only satisfy 3 conditions, 3 first properties. Okay, and because of that, RREF implies REF. Matrix in the form of RREF is also a matrix in the form of REF. Okay, these symbols is implies, implication that you learn in fundamentals of mathematics. However, the converse is not necessarily true. The converse is not necessarily true means that the converse is this. Okay, this is converse. The converse is not necessarily true. Okay, REF doesn't imply RREF. REF doesn't imply RREF. Okay. Remember, to show that some statement is not true, we have to come up with a counterexample. Remember, in fundamental of mathematics, whenever we want to show that a statement is not true, we have to come up with a counterexample. Okay, we are going to see some counterexample to show why this is not true. Okay. So, this example of a matrix is in reduced row echelon form, RREF. Why? The first property is, what is the first property? The first non-zero number must be 1, right? In the first property, we have to look at every row. The first non-zero number must be 1. So, that's in the first row. In the second row, in the third row, there is no leading one because they are all zeros. The same goes to the fourth row. Okay, so property 1 is satisfied. What about property 2? What does property 2 says? I don't remember. What does property 2 says? First, second is all rows with entirely zeros must be grouped at the bottom, right? all rows with all zeros elements must be grouped at the bottom, right? So property 2 is also satisfied. Okay, then property 3. Okay, in property 3, we have to identify all leading one. We have to identify all leading one. So here is leading one, and we have to check each pair of rows, each successive row. Okay, let's say row 1 and row 2. Leading one at the lower row is on the right side of the leading one at the upper row. So this is good. What about the other rows? We don't have to check because there is no other leading one. So property 3 is satisfied. Okay. So we know that it is REF. Because REF means that it satisfies all the first three conditions. Okay. Now property 4. Okay, now property 4. We have to check if each column. Property 4, we have to check each column. Okay, we have to find leading one, identify leading one, and we have to check column with leading one. So this is first column with leading one. This is another column with leading one. Okay. And the property says that the column with leading one, the other elements must be zeros. The other elements in the row must be zeros. So this is good. And the third row, they are all zeros. So this is also good. So property 4 is satisfied. Okay, is that clear? Thumbs up if that is clear.
Clear.
Thank you. Okay, there are some other example. You may check by your own. You may check by your own. Okay. Okay. So since they are RREF, therefore they are also REF. So the following are not in reduced row echelon form. Okay. Please check why. Please check why. Does it satisfies property 1? Does it satisfy property 1? Anyone? Or do you want me to call any name? Does it satisfy property 1?
Not.
Not. Why?
The second line after 0 is minus 1.
Yeah. In the second line or second row, after zeros must be 1. The first non-zero number must be 1, but this is not 1. So property 1 is not satisfied. Okay, then we don't have to check other properties. If property 1 is not satisfied, then we know that it is not RREF. You don't have to check other properties. Okay? You don't have to check other properties. That's it. Just find one property that is not satisfied by the matrix, and that's it. Okay. You may check the other example as well. Okay. However, okay, you may check that okay, 1, 2, 3, 4 matrices, they are not RREF. They are not RREF, but some are in REF. Which one? But some are REF. Which one? Which one is REF even though it's not RREF? Which one? The fourth one, right? The fourth one. It satisfies property 1, 2, and 3, but not property 4, right? Hold on. It does not satisfy property 3 as well. No, so not this one. This one. Right? It satisfies property 1, 2, and 3, but not 4. So it is REF, but not RREF. Okay? Okay. These are example of row echelon form. You may check. Okay. This one we'll discuss after explain elementary row operations. Okay. Another half an hour. So how is it so far? How is it so far? Is it good? Is it good?
Yes.
Thank you. Okay, so we have done two terms, augmented matrix and REF form. Now we look at the third term, elementary row operations. Remember that it is an operation that we perform on a row. Operation that we perform on a row. It is not any arithmetic operation. Okay. So, why do we need elementary row operations? Because we are able to reduce augmented matrix to a matrix of a form REF or RREF by performing some elementary row operations on the matrix. Okay, so we have augmented matrix here. Okay, this is augmented matrix. We want to reduce to a REF or RREF form. Okay, to turn the matrix into REF or RREF form, we need to do something on the matrix. We perform some zeros. As we perform some zero. Okay, that's the aim of elementary row operations. Okay, so we have to understand the elementary row operations. There are three types of elementary row operations. Let us call as ERO 1, ERO 2, and ERO 3. Okay. We are going to look at this one by one. Okay. Year one. Okay. Remember that this operation we apply or we perform on a row, not to the whole matrix, but we perform on a row only, row by row. Okay. In the first elementary row operation, we multiply a row through by a non-zero constant. We multiply the whole row with a non-zero number. Constant is real number. Okay. For example, let us consider this matrix. Now, I want to apply row 1 at the row 3. We have to identify which row we want to perform the operation. Okay, let's say I want to do something on the third row. I want to apply row 1 by using constant 5. Okay, the constants here is 5. Okay, so I multiply the whole row with 5. And this is what I got. Okay, 10, 0, minus 5. Is that clear?
Yes.
The other row remain the same. The other row remain the same. There is no changes. Okay. So I will use this notation to indicate what I have done. Okay. R3 primes means that R3 primes means that new row 3. Okay, R3 primes is new row 3. Okay, new row 3 I got by multiply all row 3 with 5. Okay, is that clear?
Yes.
Thank you. Row number 2 is very easy. We just identify 2 rows and interchange its location. We identify 2 rows and interchange its location. Okay. For example, consider this matrix and I want to perform row 2 at these 2 rows. So I simply interchange. Row 1 become row 2 and row 2 become row 1. Okay, so this is what I got. Okay, and the notation here is new. Prime means new. New row 1 is old row 2 and this one is new row 2 is equal to Supposed to be row 1, right? Row 1. Old row 1. Okay, is that clear? Is that clear?
Yes.
Okay. The third row, this is quite complicated. Row 3 is quite complicated. First of all, you have to identify which row that going to change. Which row that's going to change. Okay, which row that we are going to perform the operation on it. Okay, so first identify which row. And then to do something on that row, we need another row. We need another row. We multiply that another row with a number and then add it to the row that we identified earlier. Okay. So in one sentence, add a multiple of one row to another row. That means first thing is I have to identify row that is going to be changed. Right? Second, identify row that is going to be that is going to be multiplied with a constant. Okay, and then 3, we have to determine the constants. Okay, and for, let's say this is row K and this is row S. Okay, so, and let's say the constant is B. So what we do is we multiply B with row K, right? We multiply row K with B and then we add up to row S. Okay, is that clear? And this is new row S. Is that clear? Anyone?
Clear.
Okay. Okay. Do you need this picture? You may take a picture and then keep it because I am going to erase. Going to erase it. Okay. Bear with me. All right. So here Hold on. Hold on. Give me a second. Give me. Okay. So consider this matrix. First, I have to identify which row is going to change. Okay, I am going to change row number 2. I am going to change row number 2 by using row number 3. By using row number 3. Okay, I am going to change row number 2 by using row number 3 with a scalar with a constant 4. With a constant 4. So I multiply row number 3 with 4. Okay, and then I add to row number 2. Okay, so 4 plus 4 times 2 is 8. 8 plus 4 is 12. I have a problem with my internet. Give me 1 second. Give me a minute.
No voice, doctor.
Can you hear me?
Yes,
Yes, doctor.
yes.
Audio off. Oh. Okay. Can you hear me now?
Yes, doctor.
Okay. Mm, okay. So there's something wrong with this number. What does it supposed to be? What does it supposed to be? No answer? No answer. Okay. It's 4 times minus 1. We get minus 4 and then add up to 0. Then it is going to be minus 4. Okay, not minus 3. And we perform this operation on row number 2, right? The row number 2 change. So we perform this operation on row 2. That is why we write this as to indicate new row 2. Okay, but how to get this new row 2? We get it by using row 3, right? Because we multiply row 3 with 4. We multiply row 3 with 4 and then we add to the old row 2. Right, this is multiply old row 3 and then we add to old row 2. Okay, is that clear? And then we have
Yes,
this,
doctor.
we have a new matrix. Okay. We still have about 15 minutes. I think I'm going to finish at this.